Right now, as you're watching this video, one of the most spectacular celestial visitors in recent history is making its way through our solar system. And if you haven't heard about Comet 3I/ATLAS yet, you're about to discover why astronomers around the world are calling this the potential comet of the decade. Just last week, observers in the Southern Hemisphere reported naked-eye visibility with brightness levels exceeding initial predictions, and the latest measurements from professional observatories indicate that 3I/ATLAS is developing a tail structure that could span several degrees across our night sky by the time it reaches its closest approach to Earth. This isn't just another routine comet pass that happens every few months. This is potentially a once-in-a-generation event that could rival the great comets of the past. And the most exciting part is that we're still discovering new things about it every single day as more data comes in from both ground-based telescopes and space observatories. The Comet 3I/ATLAS, officially designated as C/2024-A3 Tsuchinshan-ATLAS, was independently discovered by two different observatories in early 2023. First by the Purple Mountain Observatory in China, which uses the Tsuchinshan name, and then by the Asteroid Terrestrial Impact Last Alert System in South Africa, giving us the Atlas portion of its name. What makes this discovery particularly fascinating is that initial orbital calculations suggested this comet has been traveling toward the inner solar system for potentially millions of years, originating from the Oort Cloud, that vast spherical shell of icy bodies that surrounds our solar system at distances up to nearly a light year from the Sun. The preliminary data shows that 3I/ATLAS follows a retrograde orbit, meaning it moves in the opposite direction to most planets and asteroids in our solar system, which immediately told astronomers that this was going to be a special object worth monitoring closely. The latest spectroscopic analysis from just this past month reveals that 3I/ATLAS is showing unusually strong emissions of cyanogen and diatomic carbon, which are responsible for the characteristic green glow that many observers are now reporting in their photographs. These chemical signatures are telling us that the comet's nucleus is rich in complex organic molecules, the same types of compounds that many scientists believe could have delivered the building blocks of life to early Earth billions of years ago. Professional astronomers using the Very Large Telescope in Chile have detected what appears to be multiple jets of material erupting from the comet's nucleus, suggesting that it might have a very irregular shape or possibly even be a contact binary, two separate bodies that merged together at some point in the distant past. What's really capturing everyone's attention right now is the unprecedented rate at which 3I/ATLAS is brightening as it approaches the Sun. Just 3 weeks ago, the comet was at magnitude 8, barely visible through binoculars. But the latest observations from this morning show it has already reached magnitude 5.2, making it visible to the naked eye from dark sky locations. If this brightening trend continues at its current rate, and that's a big if because comets are notoriously unpredictable, we could be looking at a magnitude -2 or even -3 object by the time it reaches perihelion, its closest approach to the Sun. That would make it brighter than Jupiter and potentially visible even in daylight, if you know exactly where to look. The orbital dynamics of 3I/ATLAS are particularly intriguing because this comet is what astronomers call a sun grazer, passing within just 0.4 astronomical units of the Sun, closer than Mercury's orbit. This close approach means the comet will experience intense solar radiation and solar wind pressure that could either cause it to break apart spectacularly, creating an even more impressive display, or survive intact and potentially become one of the brightest comets observed in modern history. Historical precedents like Comet Lovejoy in 2011 and Comet Ison in 2013 have shown us that sungrazers can go either way, and right now, the scientific community is divided on what will happen to 3I/ATLAS. Recent radar observations from the Arecibo Observatory's successor facilities have provided our first estimates of the comet's nucleus size, suggesting it's approximately 4 to 6 kilometers in diameter, which puts it in the moderate to large category for long-period comets. This is significant because larger nuclei tend to be more structurally stable and less likely to completely disintegrate during close solar approaches. The nucleus appears to be rotating with a period of about 12 hours, based on periodic variations in brightness that have been observed over the past several weeks. This rotation rate is actually quite important because it affects how evenly the sun's heat is distributed across the comet's surface, which in turn influences the pattern and intensity of outgassing that creates the spectacular tail we're beginning to see develop. One of the most exciting developments from just yesterday is that amateur astronomers using relatively modest equipment have begun detecting what appears to be an anti-tail, a spike of material that seems to point toward the sun rather than away from it. This is actually an optical illusion caused by our viewing angle as Earth crosses through the comet's orbital plane, and it's a phenomenon that only occurs with certain comets at specific points in their orbits. The presence of an anti-tail this early in 3I/Atlas's apparition suggests we might be in for some truly spectacular viewing geometry as the comet continues its journey through the inner solar system. The chemical composition data that's been gathered so far is revealing some surprising details about where 3I/Atlas might have formed and how long it's been traveling. The ratio of different isotopes of water ice detected in the comet's spectrum suggests it formed in a region of the early solar system that was colder than where most Jupiter family comets originated. This points to an origin in the Oort Cloud, but even more intriguingly, some researchers are suggesting that 3I/Atlas might actually be an interstellar interloper, captured by our sun's gravity millions of years ago. While this is still a minority view and would require more data to confirm, the possibility has generated considerable excitement in the astronomical community. Professional observatories around the world have now coordinated their efforts to maintain 24-hour surveillance of 3I/Atlas as it approaches perihelion. The Solar and Heliospheric Observatory, or SOHO, spacecraft is perfectly positioned to observe the comet's close approach to the sun, and its coronagraph instruments will be able to track 3I/Atlas even when it's too close to the sun for ground-based telescopes to observe safely. This continuous coverage is crucial because comets can undergo sudden outbursts or fragmentation events with little warning, and capturing these events as they happen provides invaluable data for understanding cometary physics. The latest models of 3I/Atlas's dust production rate, based on infrared observations from the Spitzer Space Telescope successor, the James Webb Space Telescope, indicate that the comet is currently shedding approximately 100 tons of material per second. This might sound like a lot, but it's actually quite typical for a comet of this size at this distance from the sun. What's unusual is the composition of this dust, which appears to be richer in silicates and poorer in water ice than expected, suggesting that 3I/Atlas might have experienced significant thermal processing during a previous close approach to a star, either our sun or perhaps another star if the interstellar hypothesis proves correct. Amateur astronomers are playing a crucial role in tracking 3I/Atlas, with thousands of observations being submitted daily to the Minor Planet Center and other astronomical databases. These citizen scientists are providing valuable data on the comet's brightness variations, tail development, and any unusual features that might appear. Just last night, an amateur astronomer in Australia captured what appears to be a disconnection event in the comet's ion tail, where a section of the tail was severed by interaction with a solar wind and drifted away from a comet. These events are relatively rare and provide important information about the solar wind conditions in the inner solar system. The timing of 3I/Atlas's appearance is particularly fortuitous because it coincides with several major astronomical events this year. The comet will be visible during the upcoming solar eclipse season, potentially providing a rare opportunity to observe a bright comet near the Sun during totality. Additionally, 3I/ATLAS will pass relatively close to several bright stars and even some deep sky objects, creating fantastic photographic opportunities for astrophotographers. The comet's path will take it through some of the most photogenic regions of the sky, including passages near the Pleiades star cluster and the Orion Nebula region. Scientific teams are already preparing specialized instruments to study 3I/ATLAS during its closest approach. Several high-altitude balloon missions are being planned to observe the comet from above most of Earth's atmosphere, where they can detect ultraviolet and infrared emissions that don't reach ground-based telescopes. These observations will help scientists understand the comet's molecular composition in unprecedented detail, and might even detect complex organic molecules that could provide clues about the origin of life on Earth. The potential for 3I/ATLAS to become a great comet visible to billions of people worldwide has generated significant media attention, but it's important to manage expectations. Comets are notoriously unpredictable, and many factors could affect how impressive 3I/ATLAS ultimately becomes. The comet's brightness depends not just on its intrinsic properties, but also on how it responds to solar heating, whether it experiences any fragmentation events, and the viewing geometry from Earth. Historical examples like Comet Kohoutek in 1973, which was predicted to be spectacular but ended up being relatively disappointing, remind us to be cautiously optimistic. Part 2. The theoretical models being developed to predict 3I/ATLAS's behavior are incorporating decades of cometary science and the latest computational techniques, including machine learning algorithms trained on data from hundreds of previous comet apparitions. These models suggest that 3I/ATLAS has approximately a 60% chance of surviving its close solar approach intact, with the remaining 40% split between partial fragmentation, which could actually enhance the comet's brightness temporarily, and complete disintegration, which would end the show prematurely. The key factor appears to be the structural integrity of the nucleus, which depends on factors like its density, composition, and internal structure that we can only estimate based on indirect observations. Current research into 3I/ATLAS is revealing fascinating connections to our understanding of solar system formation and evolution. The comet's orbital parameters suggest it's making its first passage through the inner solar system, at least in recorded history, which means we're seeing pristine material that has been preserved in the deep freeze of space for billions of years. This makes 3I/ATLAS a time capsule from the early solar system, and every observation we make provides clues about the conditions that existed when the planets were forming. The detection of certain noble gases in the comet's coma, announced just this week by researchers using specialized spectrographs, indicates that 3I/ATLAS formed in an extremely cold environment, possibly at temperatures below 20 Kelvin. The dust trail analysis from 3I/ATLAS is providing unexpected insights into the comet's past activity. Using sophisticated computer models that track individual dust particles ejected from the comet over thousands of years, researchers have identified what appears to be evidence of previous outbursts or fragmentation events, even though this is supposedly the comet's first passage through the inner solar system. This paradox has led to several competing theories, including the possibility that 3I/ATLAS experienced close encounters with other stars before entering our solar system, or that it underwent thermal processing from radioactive decay of short-lived isotopes in its interior. Professional astronomers are particularly excited about the opportunity to study 3I/ATLAS using the full suite of modern astronomical instruments that weren't available during previous great comet apparitions. The Atacama Large Millimeter Array in Chile has been detecting complex organic molecules in the comet's coma, including methanol, formaldehyde, and even more complex species like glycine precursors. These observations are providing direct evidence for the types of chemical reactions that occur in cometary ices when they're exposed to solar radiation, processes that might have been important for delivering organic molecules to the early Earth. The latest radar observations of 3I/ATLAS have revealed something unexpected about the comet's surface properties. The radar echo suggests that the nucleus is covered with a layer of extremely porous material, possibly with a density less than that of fresh snow. This fluffy surface layer, which might be several meters thick, could be the result of billions of years of cosmic ray bombardment in the outer solar system, creating a fragile matrix of organic polymers and mineral grains. Understanding this surface layer is crucial for predicting how the comet will respond to intense solar heating during perihelion passage. Space agencies around the world are scrambling to adjust their existing spacecraft observations to include 3I/ATLAS in their targeting schedules. The Parker Solar Probe, which is currently making close approaches to the Sun, might be able to observe 3I/ATLAS from a unique vantage point inside Mercury's orbit, potentially detecting particles and fields associated with the comet's interaction with the solar wind. The European Space Agency Solar Orbiter is also well positioned to observe the comet, and its instruments could provide unprecedented views of how the comet's tail forms and evolves in response to changing solar wind conditions. The citizen science response to 3I/ATLAS has been extraordinary, with new online platforms being developed specifically to coordinate observations and share data. These platforms are allowing amateur astronomers to contribute scientifically valuable observations that complement professional studies. For example, the global network of amateur observers can provide nearly continuous coverage of the comet's brightness, something that would be impossible for professional observatories alone to achieve. This collaborative approach between professionals and amateurs represents the future of cometary science and is already yielding important discoveries about 3I/ATLAS's behavior. Recent spectroscopic observations have detected an unusual abundance of carbon chain molecules in 3I/ATLAS's coma, including species like C3 and C4 that are relatively rare in most comets. This carbon-rich composition has led some researchers to classify 3I/ATLAS as a carbon chain depleted comet, which might indicate formation in a different region of the protoplanetary disk than typical comets. The implications of this classification are still being debated, but it could mean that 3I/ATLAS represents a previously unknown reservoir of cometary bodies in the outer solar system. The gravitational perturbations that 3I/ATLAS has experienced during its journey through the solar system are being carefully tracked to refine predictions of its future orbit. Current calculations suggest that if the comet survives perihelion, it will be ejected from the solar system on a hyperbolic trajectory, never to return. This makes the current apparition truly a once-in-a-lifetime event, as 3I/ATLAS will leave our solar system forever after this single passage. The exact trajectory depends on non-gravitational forces caused by outgassing from the nucleus, which are still being measured and modeled. Laboratory experiments designed to simulate conditions on 3I/ATLAS's surface are providing insights into the physical and chemical processes occurring on the comet. Scientists are using vacuum chambers cooled to near absolute zero and bombarded with ultraviolet radiation to recreate the environment the comet experiences. These experiments have shown that certain organic molecules can form spontaneously under these conditions, supporting theories about comets as factories for prebiotic chemistry. The specific molecules detected in 3I/ATLAS's spectrum match well with those produced in these laboratory simulations, validating our understanding of cometary chemistry. The potential cultural impact of 3I/Atlas is already being felt, with the comet featuring in discussions about space exploration, planetary defense, and even philosophy. If 3I/Atlas becomes as bright as predicted, it will be the first great comet visible to most of humanity since the widespread adoption of smartphones and social media, potentially creating a global shared experience unlike anything we've seen before. Museums and planetariums worldwide are preparing special programs about 3I/Atlas, and the comet is already inspiring artists, musicians, and writers to create works celebrating this celestial visitor. Educational initiatives centered around 3I/Atlas are helping to teach millions of people about comets, the solar system, and astronomy in general. Schools are incorporating comet observations into their science curricula, and online courses about 3I/Atlas are attracting thousands of students. This educational aspect is particularly important because it's creating a new generation of astronomy enthusiasts who might be inspired to pursue careers in science. The comet is serving as a gateway for public engagement with astronomy, demonstrating the power of celestial events to capture human imagination and curiosity. The latest thermal modeling of 3I/Atlas's nucleus suggests that the comet is experiencing differential heating that could lead to spectacular jets and fountains of material as it approaches the Sun. These models, based on the nucleus's rotation rate and assumed shape, predict that certain regions of the comet will experience rapid temperature changes that could trigger explosive outgassing events. If these predictions are correct, we might see dramatic changes in the comet's appearance over very short timescales, possibly even visible to naked eye observers, as sudden brightenings or changes in tail structure. International collaboration on 3I/Atlas observations has reached unprecedented levels, with data sharing agreements between observatories that rarely work together. This cooperation is enabling round-the-clock monitoring of the comet and ensuring that no important events are missed. The International Astronomical Union has established a special working group dedicated to 3I/Atlas, coordinating observations and ensuring that data is quickly disseminated to the global scientific community. This level of cooperation serves as a model for how the astronomical community can work together to study transient celestial events. Part 3. The technological advances being driven by 3I/Atlas observations are pushing the boundaries of what's possible in cometary science, with new instruments and techniques being developed specifically to study this comet. Adaptive optic systems at major observatories are being optimized to track 3I/Atlas's rapid motion across the sky, allowing for unprecedented high-resolution imaging of the comet's inner coma, and potentially even resolving details on the nucleus itself. These technological improvements will benefit future comet observations long after 3I/Atlas has left our solar system, representing a lasting legacy of this remarkable apparition. Theoretical physicists are using 3I/Atlas as a test case for new models of cometary dynamics that incorporate quantum mechanical effects at the molecular level. These models suggest that certain chemical reactions in the comet's coma might proceed differently than expected based on classical chemistry, potentially explaining some of the unusual spectral features observed in 3I/Atlas. While these quantum effects are subtle, they could be important for understanding the formation of complex organic molecules in cometary environments, and might have implications for astrobiology and the origin of life. The economic impact of 3I/Atlas is already being felt in the astronomy tourism industry, with dark sky locations around the world preparing for an influx of visitors hoping to see the comet. Hotels in remote areas with excellent viewing conditions are reporting booking rates not seen since the last total solar eclipse, and specialized comet watching tours are being organized by astronomy clubs and travel companies. This economic activity demonstrates how celestial events can have real-world impacts beyond their scientific value, supporting local communities and promoting science education through tourism. Recent observations of 3I/Atlas's plasma tail have revealed complex structures that are providing new insights into the solar wind and the sun's magnetic field. The comet's tail acts like a wind sock in space, showing us the direction and strength of the solar wind at different locations in the inner solar system. Disconnection events and kinks in the tail are revealing the passage of coronal mass ejections and other solar phenomena, making 3I/Atlas a valuable probe of space weather conditions. These observations are being coordinated with spacecraft monitoring the sun to create a comprehensive picture of solar-terrestrial interactions. The astrobiological implications of 3I/Atlas are generating considerable excitement among researchers studying the origin of life. The detection of phosphorus-bearing molecules in the comet spectrum, announced just last week, adds to the growing evidence that comets could have delivered all the essential elements for life to the early Earth. Phosphorus is particularly important because it's a key component of DNA and RNA, and its relative scarcity on Earth has long been a puzzle for origin of life researchers. The abundance of phosphorus in 3I/Atlas suggests that cometary delivery could have solved this problem for early life. Numerical simulations of 3I/Atlas's nucleus are revealing the complex interplay between different physical processes that control the comet's activity. These simulations must account for heat conduction through the porous nucleus, sublimation of different ice species at various temperatures, gas flow through the porous surface layer, and the acceleration of dust grains by the escaping gas. The latest models suggest that 3I/Atlas's activity is being driven primarily by carbon monoxide sublimation at its current distance from the Sun, but this will transition to water ice sublimation as it approaches perihelion, potentially causing a dramatic increase in activity. The polarimetric observations of 3I/Atlas are providing unique information about the physical properties of dust grains in the comet's coma. The way sunlight is polarized when it scatters off these dust grains depends on their size, shape, and composition, allowing astronomers to infer these properties from careful measurements. Recent polarimetry suggests that 3I/Atlas is producing a population of very fluffy, aggregate dust grains that are quite different from the more compact grains seen in some other comets. This could indicate differences in how the dust formed or evolved in 3I/Atlas's nucleus compared to other comets. Archive searches have revealed possible prediscovery observations of 3I/Atlas in survey images dating back several years, when the comet was much fainter and farther from the Sun. These prediscovery observations are valuable for refining the comet's orbit and understanding its long-term brightness evolution. They also demonstrate the importance of maintaining comprehensive astronomical archives that can be searched for objects that weren't recognized at the time the images were taken. The recovery of 3I/Atlas in these archival images required sophisticated image processing techniques and represents a triumph of modern computational astronomy. The interaction between 3I/Atlas and the solar wind is creating a natural laboratory for studying plasma physics under conditions that can't be replicated on Earth. The comet's ionized gas tail is subject to complex electromagnetic forces that cause it to develop intricate structures, including rays, streamers, and knots. High-resolution observations of these structures are testing our theoretical understanding of plasma instabilities and magnetic reconnection, processes that are important not just for comets, but for many astrophysical phenomena, including solar flares and stellar winds. ground-based radio observations of 3I/ATLAS are detecting emissions from various molecular species in the comet's coma, including some that are difficult or impossible to observe at optical wavelengths. The detection of hydrogen cyanide, methanol, and other molecules at radio wavelengths is providing complementary information to optical and infrared observations, creating a more complete picture of the comet's composition. These radio observations are particularly valuable for detecting parent molecules that quickly break down into fragments when exposed to solar ultraviolet radiation. The latest dynamical models suggest that 3I/ATLAS might be part of a family of comets that share similar orbits, possibly fragments of a larger body that broke apart thousands or millions of years ago. While no other members of this hypothetical family have been definitively identified, searches are underway for faint comets that might be dynamically related to 3I/ATLAS. If such a family exists, it would provide valuable insights into cometary fragmentation processes and could help us understand the size distribution of bodies in the Oort Cloud. Spectroscopic monitoring of 3I/ATLAS is revealing how the comet's chemical composition appears to change as different ices sublimate at varying distances from the Sun. This compositional evolution is providing a kind of stratigraphic record of how the comet's nucleus formed, with different layers containing different mixtures of ices and dust. The current observations suggest that 3I/ATLAS has a relatively homogeneous composition, unlike some comets that show dramatic compositional changes as they approach the Sun, indicating that its nucleus might have formed quickly from well-mixed materials in the early solar system. The possibility that 3I/ATLAS could fragment as it approaches the Sun has prompted contingency planning for rapid response observations if such an event occurs. Fragmentation events can happen with little warning and evolve quickly, requiring coordinated observations to capture the crucial early stages. Several observatories have agreed to interrupt their regular programs immediately if 3I/ATLAS shows signs of breaking apart, and amateur astronomers are being encouraged to monitor the comet frequently for any signs of unusual activity that might presage a fragmentation event. Theoretical work on 3I/ATLAS is exploring the implications of its orbit for our understanding of the Oort Cloud and the outer solar system. The comet's orbital parameters suggest it originated from a region of the Oort Cloud that has been little studied, potentially sampling a population of comets with different formation histories than the short-period comets we observe more frequently. This could mean that 3I/ATLAS represents a different epoch of solar system formation or a region of the protoplanetary disk with unusual conditions, expanding our understanding of the diversity of small bodies in our solar system. The cultural and historical significance of 3I/ATLAS is already being documented by historians and anthropologists studying how different cultures around the world are responding to the comet's appearance. Unlike historical comet apparitions that were often interpreted as omens or portents, the modern response to 3I/ATLAS is characterized by scientific curiosity and wonder, reflecting humanity's evolved understanding of these celestial visitors. Social media analysis shows that 3I/ATLAS is generating predominantly positive responses, with people sharing observations, photographs, and scientific information rather than fearful or superstitious interpretations. Environmental monitoring during 3I/ATLAS's passage is providing a unique opportunity to study how a bright comet might affect Earth's upper atmosphere. While the comet won't come close enough to Earth to have any direct effects, the increased interest in night sky observation is leading to discussions about light pollution and the importance of dark skies. Some communities are implementing temporary lighting restrictions to improve comet visibility, demonstrating how astronomical events can promote environmental awareness and action. These efforts might have lasting benefits for astronomy and wildlife long after 3I/Atlas has departed. The legacy of 3I/Atlas will extend far beyond its brief appearance in our skies, influencing cometary science, public engagement with astronomy, and our understanding of the solar system for years to come. The data collected during this apparition will be analyzed for decades, potentially revealing new insights as our theoretical understanding and computational capabilities improve. Young people inspired by 3I/Atlas might become the next generation of astronomers and planetary scientists, continuing the chain of discovery that connects us to the cosmos. As we watch 3I/Atlas blaze across our skies, we're not just observing a comet. We're participating in a moment of collective human experience that transcends borders, cultures, and languages, reminding us of our shared heritage as inhabitants of a small planet orbiting an ordinary star in a vast and wonderful universe. The story of 3I/Atlas is still being written, and every observation, every photograph, and every measurement adds another chapter to this remarkable tale of cosmic exploration and discovery.